So welcome everybody again to our weekly seminar, right? And it's a great pleasure to have back Nemanja Draganić, who not so long time ago was here in Zurich. And he will talk about Hamiltonicity of expanders. Please, Nemanja.
Thank you, Benny. So also thank you for inviting me to this great seminar. So I was able to tune in to some talks and it was really very nice talks. So I hope I can also say something nice. So I'll, as Benny said, present some results on Hamiltonicity, which I had together with Richard, David, and Alexei, and Benny. So let's talk about Hamiltonicity. So a graph is Hamiltonian if it contains a Hamilton cycle, and a Hamilton cycle is just a cycle which contains every vertex of the graph. And this is one of the best studied notions in combinatorics. And actually this question where you have the input graph and you want to determine if it's Hamiltonian, it is a computationally very hard question. So in fact, it's NP complete. And then one of the things which you do with such questions, or one direction of research, say in this particular instance, you try to find really simple conditions which imply Hamiltonicity. So just to illustrate what I mean, so here we have three conditions. The first one by Dirac, which says that if the minimum degree is at least n½ then your graph is Hamiltonian. So n will always be for me the number of the vertices of the graph which I look at. So Dirac gives a minimum degree condition. Then we have this result of Hvatal and Erdős, which is really beautiful. It connects the connectivity and independence numbers. So if the connectivity is at least the independence number, then your graph is Hamiltonian. And then also this result of Jackson from 1980. So it says that if your graph is too connected, is k-regular and has less than 3k vertices, then it's Hamiltonian. And so these results have something in common. Actually, most of these results, which give simple conditions, have something in common. And this is that they imply that the graph is actually already very dense. And as you can imagine, if the graph is dense, then it's easier to find structure inside of it. So in particular, Dirac and Jackson here imply a linear average degree. And if you think for a minute, Hvatal Erdős will imply that the that the average degree is of order at least roughly root n. Okay, and then a very natural question is, do we have some conditions for sparse graphs? So conditions which imply that sparse graphs are Hamiltonian. And now a natural direction, a first step, say, is to consider random graphs. So there was this result of Poshai from 76 already, which considers so let's say, look at the binomial random graph GNP. So you have n vertices and each edge is there with probability p independently for all other edges. And then if p is at least some big constant times log n over n, then we know that the graph is Hamiltonian. And this is actually close to optimal. So basically, this is optimal up to this constant. And so I'll mention just one more result in this direction, which basically gives a more precise result by Bolobash and independently Kongush and Semeredi. And they show basically the sharp threshold. So basically, if p is log n plus log n over n, a little more above it, you have Hamiltonicity, and a little more below it, you'll actually have a vertex which has degree strictly less than 2. So you'll not be Hamiltonian. So the GMP we understand quite well, but what about other random graph models? Here I'll briefly mention random regular graphs. So we now precisely know the state of the art. So basically in the early 2000s we knew that all relevant d-regular graphs are Hamiltonian. So random d-regular graphs. So, and what I mean by this is that if you draw a d-regular graph from all d-regular graphs uniformly at random with high probability, meaning with probability tending to 1 as n tends to infinity, you will have a Hamilton. Okay, so we know basically the state of the the state of the art in random graphs. We basically solved random graphs in some sense. So, but something which I want to mention about all of these results about random graphs is that really randomness in these papers is heavily exploited. So it's not like we look at these random graphs and we look at we find some nice pseudo-random property of them, and then we prove that graphs with this property have Hamilton cycles. It's really that we inherently exploit randomness. And then the natural question is, do we have some nice deterministic properties for sparse graphs, which would imply Hamiltonicity? And so a natural direction to study is to look at pseudo-random graphs. So what are pseudo-random graphs? So these are deterministic graphs, really. You have some deterministic property, and they kind of resemble random graphs in those properties. And so they're studied since the 80s, and there's many different notions which measure how much a graph looks like a random graph. And one of the most popular notions is that of ND lambda graphs. And so if you didn't see ND lambda graphs, the definition, it doesn't matter. So I'll give you some nice properties of them. I'll just, for completeness, I'll tell you the definition. So a graph is an ND lambda graph if it has n vertices, it's deregular. And if you look at the eigenvalues of its adjacency matrix, so the first one is, the biggest one is always D, where the graph is deregular. And if all the others are in absolute value less than lambda, then your graph is a ND lambda. And so now I'll give you something which is easier to grasp if you didn't see this definition. So something which you can prove about ND lambda graphs is something called the expander mixing lemma. And the expander mixing lemma just tells you something about the edge distribution of the graph. And so what is it precisely? So between every two sets of vertices, you look how much it deviates from the expected number of edges you would have in a random graph. And this is bounded by this factor lambda times root size of A times size of B. So you see, so you just measure the deviation from the expectation, and this lambda here controls how much you deviate. So the smaller the lambda, the better your graph resembles a random graph. Okay, so now I just even more to understand better the properties of such graphs, I want to extract two simple consequences from the expander mixing lemma. So one of them is vertex expansion of sets. So for every set, essentially you have that if you look at its external neighborhood, the size of it will be roughly by a d over lambda squared factor larger than the set itself. Okay, so this is an easy consequence of the expander mixing lemma. And another one, which she also can prove, is that if you have two large enough disjoint sets, you'll always have an edge in between. Okay, so now we kind of have a good grasp of these ND lambda graphs, and there was a result by Michael and Benny from 2003, I think, which says that if this d over lambda, called the spectral ratio, is at least is at least something of order log n, then your graph is Hamiltonian. And just to give some perspective, to look back at this properties which we had here. So if you look at here, say the vertex expansion. So if d over lambda is at least log n, then you would have, say, vertex expansion by a log squared factor. So essentially, if you expand by log squared, then you're Hamiltonian. But they really need the expander mixing lemma in the proof. Okay. And in the same paper, they had a beautiful conjecture which essentially says that if this d over lambda is at least a big constant, then your graph is Hamiltonian. So you can think of it, if you have even a little bit, just a big constant expansion, then you would be Hamiltonian. But okay, so this was the conjecture from 2003, and that 20 years there was nothing on this. Even this result had many applications, and really many people looked at this question because it's very natural, but there was no progress until very recently, where Stefan, David, and Benny actually improved this to log to the 1/3. And even though the full conjecture seemed out of reach, there was one conjecture which was even stronger and appeared in some papers, and is kind of the natural and basically the ultimate conjecture you can hope for in such expander graphs. And just to state this conjecture, I'll define you a C expander. So a C expander is basically a graph which has the following properties. So it has vertex expansion. So every set of size n/2, C expands by a factor of C, and you have an edge between two large enough sets, let's say of size at least n/2C. And you can see these are the properties which are basically following from the expander mixing lemma. So these two nice properties which follow from the expander mixing lemma, but the expander mixing lemma is really something something stronger than these two properties. It gives you really a strong property on the edge distribution. Okay, so I defined the C expander, and then the conjecture which I was mentioning is that for every large enough constant, every C expander is Hamiltonian. So just vertex expansion and edges between large enough sets should be already enough for Hamiltonicity. And the best known result in this direction was by Hefetz, Krivelevich, and Sudakov, I think 2014, which gives that if you have roughly log n expanders, then your graph is Hamiltonian. Okay, so our contribution is actually the resolution of this conjecture. So we show that actually for that C expanders are Hamiltonian for a large enough. And so this result has many applications. I'll just mention some of them. So the first application is it immediately resolves the Krivelevich Sudakov conjecture. So if your spectral ratio is at least some big constant, then your ND lambda graph is Hamiltonian. So for the next application I want to mention, so first I'll state this Lovaas conjecture, which is another conjecture about Hamiltonicity and is still widely open, which says that every connected vertex transitive graph is Hamiltonian except some small few examples. And what vertex transitive means is just that for every pair of vertices, you have an automorphism of the graph which says which sends the first one to the second. Okay, so and to give further context, there was in the 90s there was a result by Allen and Reuchmann, this application will be something about Cayley graphs. So if you don't know what Cayley graphs are, it also doesn't matter. So the talk is not about this, just for you who know. So Cayley graphs are basically graphs which come from algebraic construction. So you have a group, and I take a subset of the elements and I generate a Cayley graph. And actually, if I take this subset which generates me my Cayley graph at random, so I take, let's say, big constant times log of the size of the group, many elements, then Allen and Reuchmann showed that the Cayley graph which is generated by it is connected. Okay, so since such graphs are connected, and we know that Cayley graphs are vertex transitive, so this is a specific instance of the Lovaas conjecture to see actually if such graphs, such Cayley graphs, are Hamiltonian. And this was actually conjectured by Pak and Radojcic. So exactly, if you take constant times log g many elements is the graph Hamiltonian, and actually it follows quite straightforwardly from our methods that this is actually the case. So we confirmed the Pak-Radojcic conjecture. So for another application, so we look at proper edge colorings of the complete graph. And so what we now want is a Hamilton cycle which uses few colors. And Akbari et al. Actually showed that you can do it, so you can find a Hamilton cycle which only uses at most 8 root n colors. And then there was the result of Bala, Pokrovskiy, and Sudakov, which shows that you can do it with only log to the 3 many colors. Then from the result which I mentioned by Stefan, David, and Benny, you can do it with log to the 5/3. And what we show, and actually resolving a conjecture by Akbari et al. And proving basically an optimal result up to a constant factor. So you can actually find the cycle with at most log n many colors. So maybe I didn't say here, I'm always looking at properly edged colors, and I'm always looking at optimal colors, optimal coloring, so the bit the smallest number of colors. Okay. Okay, maybe I skipped this one. So there's many more applications, and so in game theoretic instances, and basically anywhere in graphs where you want to find long paths which are spanning, you can apply our machinery. So now I actually want to go into the proof and really tell you kind of an overview of the proof, and really goes in a few places into maybe small technical details, just to give you a flavor of the methods which we use. So first I want to talk a bit about Poisson rotation. So you remember this result of Poisson, which determines the weak threshold for Hamiltonicity in random graphs. It's not only important because it solves this problem, but the method which was developed there is kind of a cornerstone of many results on Hamiltonicity over the years. So I really want to now briefly review or to see how Poisson rotation works. This can be found basically in many textbooks on graph theory. And then I want to tell you why this basic approach fails in some sense in expanders. And I'll show you how to modify it so that you can get something. Okay, so let's say you want to get a Hamilton cycle, or you want to get a long path in your graph. So potentially a Hamilton path or Hamilton cycle. So what conceivable strategy is start with some path and make it longer and longer until you reach the desired length. And so how you can do it is, so say P is one of the is a longest path. And then one thing which you can notice is that if you look at an endpoint, if you look at its neighbors, no neighbors can live outside of the path, because if you had a neighbor outside, you would have a longer path. Okay, so no neighbors outside, but let's say we are working in connected graphs, then I want to claim that also there's no edges between the endpoints of longest paths. Why? Because then you would get a cycle, and if the graph is connected, then there's a vertex which has a neighbor on the path, on the cycle, and then you would have a longer path like this. So you would extend it by one. So okay, all the neighbors are somewhere in the interior of the path. And then one trivial thing, but important thing to notice is if you look at the neighbor to the left of this vertex here, this red vertex, then it's again an endpoint of a longest path. Okay, you can just do this process of removing this edge here and adding this new edge, and then you would get again a longest path, and this would be a new endpoint. And this process of doing this we call a rotation. Okay. So now just to start working a bit, so to, let's say, to give some framework, let's say we work in a binomial random graph. Exactly, Benny, okay. Sorry, you've been keeping popping up on my screen, so now it's fine. Okay, so yes, so say we work in a binomial random graph, and exactly as in the setting of Poisson, so say your average degree is big constant times log n, and let's try to find a long path inside of such a graph. So look at the longest path, look at the vertex here, which is an endpoint, and look at all of its neighbors. And now for each of these neighbors, this we go one step to the left, and then you'll get a new endpoint of a longest path, and this set we call S1. Okay, so S1 are the endpoints after just one rotation, and since the average degree is d, then we can, by some concentration, we know that S1 is roughly of size d. Then if you look at S2, which are, so the same, so for each vertex in S1, you can again do this rotation. And so for each one of them, you have again d vertices. And since our graph is an expander, one can show that this set S2, which are endpoints after two rotations, is of roughly size d squared. And you see now you can use this expansion property until you reach some set Si of vertices, which are the endpoints after I rotations, and this Si will be of linear size. So you can only do log n many steps until you reach linearly many vertices, which are endpoints of some longest path. Okay, so now let's exploit this. So fix some longest path where the endpoints are v and x, and fix this x and start rotating from v. So do this procedure which I did before. So you rotate from v, and then you obtain a set of vertices, say s, such that y, x are the endpoints of a longest path. Okay, and s is of linear size. Okay, so you can do these rotations. X will always be fixed. You'll never reach it by rotations, by the property that there's no endpoints. There's no edges between endpoints. And so x will remain fixed, and you'll get linearly many y's for this x. But now you can do the same. So you can now, but on the other side, you can now fix each of those y's, and in their path you're rotating from x. So what you can do is for each y, fix y, rotate from x, and then what you would get is, let's say, a set sy, such that for each z which you have in sy, you have a longest path where y is an endpoint and z is an endpoint. So for each y, you will have linearly many z's. Okay? So what this means basically is that we'll have quadratically many pairs which are endpoints of a longest path. Okay, so for x, we got linearly many y's, and for each of these linearly many y's, we got linearly many z's. Okay, so we have quadratically many pairs, and now I want to give the finishing touch. So here, so we use something which is called the sprinkling method in random graphs. So basically, you just add a few random edges which won't change your edge probability by too much. So let's say big constant times log n many random edges. And then by standard concentration bounds, because I have n squared many pairs really, which are good for me. And any edge between such a pair would be closing a cycle as before. There is one edge with high probability which closes a cycle, and then we can prolong the path. Okay, so you can do this obviously once, but you can also do this n many times, because you start with some path and you're always making it by one longer. So you can repeat this process many times. And then in the end, you would get a Hamilton cycle. Okay, so now I showed you this method in random graphs. This was known for 50 years. Why can't I now use this in expander graphs? And the answer is, so first, you see, expander graphs have this expansion property. I can do this expanding and post the rotation to get many endpoints, and I can get this quadratically many pairs. Okay, so this I already have in expanders. And I also have edges between two large enough sets. So why am I not done in expanders? And the answer is, so these pairs which I get here, I don't have any control on them. It's not really vertices between two large linear sets. It's just an arbitrary collection of n squared pairs. And for such an arbitrary collection, because I don't have any control, I don't know if there's an edge in this collection of pairs. Okay, so I can't use this in expanders, then I have to find another way to modify maybe Poisson rotation. And
excuse me, Nemanja. I thought in the definition of your like C expander, you assume between every two large set there is at least one edge. No?
yes.
But then I thought the problem comes from the former stage that you cannot easily prove that, for example, S7 has no large intersection with that.
Say that S what?
Like you're growing, like for example, you fix X, you are growing the set of Y so that can be an endpoint. And then I guess it's not easy to have a good control of the size of the S. Is this the
So here,
obstacle
if you just do the procedure as I described here, okay?
Yeah.
So you'll get a large set S, okay?
Yeah.
And each of these sets, vertices in the S, has its own set SY. It's not really a product structure.
Right. Sorry. Yeah, it's correct. Yeah.
Yes. So this is, and thank you. So this is exactly the problem. So it's not really an edge between two large enough sets. It's every Y has its own set. So it's really, you have no control.
But the former step is fine.
Yes, exactly. So you can do expansion in the same way as you did before. Yes, so you can get this S and SY, but you can't really, so you get these n squared many pairs, but you can't really have a product structure. Okay. So now let's go a bit, give a setting in which we work. So I want to work with linear forests, and I want to introduce rotation in linear forests. So why linear forest? Why do I want to look at linear forests? So one conceivable strategy, if you want, say, a Hamilton cycle or a Hamilton path, is to look at a linear forest in your graph, which is spanning. So a linear forest is just a collection of disjoint paths. So you look at the spanning linear forest, and you want to look at the linear forest which has the fewest number of paths, the smallest number of paths. And then maybe doing some transformations, you can decrease the number of paths in this linear forest. And if you can maybe continue doing this up until you have just one path, say, then this would be a conceivable strategy. Okay, so that's why I want to introduce rotation in linear forests. So look at one endpoint of one of those paths, and let's say it has a neighbor inside of one of the other paths. Okay, and then consider the vertex, let's say the neighboring vertex of this vertex which you found, and then what we call a one rotation is just replacing these two paths from the beginning with this purple and this green path. Okay, you just remove this edge here and you add this edge here. And so one interesting, trivial but interesting property here is that if you look at the obtained linear forest, just this vertex here changed. So it's actually not an endpoint anymore. And this vertex here is an endpoint of the newly obtained linear forest. So you remove this as an endpoint and you add this as an endpoint, and every other endpoint stayed the same. Okay, so this is an old endpoint. This vertex we call a pivot, and this vertex we call the new endpoint. Okay, so nothing spectacular happened. And now I want to define a K rotation, which is just a sequence of one rotations, but in a special way. So you do a one rotation, you have this old endpoint, you have this new endpoint, and then you do a rotation where this new endpoint is an old endpoint. So you again do a rotation, you get another new endpoint, and then you get another one, and then you get another one, and then you do this K times, and this is a K rotation. And now a simple, again, but crucial property, and this you should remember for the rest of the talk. What happened here is if you look at the endpoint changes, only this vertex X with which we start, it disappeared from the set of endpoints. And this last new endpoint Y is a new endpoint. Everything else stays the same. And why is this the case? Because we replace this one with this one, because it's a one rotation, then we replace this one with this one, we replace this one with this one, and in the end, we replace this one with this one. So in the end, what happened is we replace just x with y. Okay, so rotations in linear forest just change one endpoint for another one. Okay, so now let me talk a bit about how possibly you can use this. So let's say you have a linear forest, and let's say we maybe split the paths in three sections. So we have some paths here, and then we have two clusters here of paths, and let's say these two clusters of paths have linearly many vertices. Okay, one thing, and it's just a technical thing which is easy to do. So if you just restrict your attention to something which has linearly many vertices, we don't know if such a graph, the subgraph is an expander. So subgraphs of expanders don't necessarily inherit expansion. But what you can do is a simple cleaning procedure where you just remove a few vertices. And what is left, let's say this purple graph, is a C prime expander where C prime is slightly worse constant in C. Okay, so you do this, and so one thing which I want to do is to decrease the number of paths in such a linear forest. And let's say, and this would be a dream case, say, that I have two vertices, let's say x, which is an endpoint here, which has a neighbor inside of the first expander, and I have y, which has a neighbor inside of the second expander. So I get these endpoints x prime and y prime by doing this one rotations. And now what I can do is, since these two vertices, these two endpoints, live on paths which are completely disjoint, and these C prime expanders live on paths which are completely disjoint, I can now start doing Poisson rotation inside of the expanders themselves. So I can repeat basically the same procedure which I showed you before, and I can get a set of vertices Sx which I can reach from x prime, and a set of vertices Sy which I can reach from y prime. Okay, and these sets are of linear size. Okay, so I just rotate inside of these parts, and because they are of linear size, and now they're really disjoint sets of vertices, I can find an edge between Sx and Sy. Let's say I call it x star and y star. Okay. So what happened here, basically, just to again see what happened here, is I changed this endpoint x for an endpoint x prime, and I changed this y with an endpoint y prime. I did some rotations until I reach x star here, the specific vertex x star. And here I did some rotations till I reached this vertex y star, and I have an edge here. So what happened, like globally, what happened is I changed this endpoint with this endpoint, I changed y with y star. So no other endpoint changes happened, and now I found an edge between x star and y star. And what this basically means is, because I killed x star and y star, the endpoint changes is just that I killed x, and y. And this is the only thing which happened globally. And now I decrease the number of paths of a linear forest by decreasing the number of endpoints, and I maybe can continue doing this. So maybe here to note, it gets slightly technical, but say one of the reasons why I really want these paths to be on disjoint set of Earth. Why I want these expanders to be on disjoint paths is because let's say that they were not on disjoint paths, and I did these rotations. Then let's say this x star and y star, which I found in the end, they could possibly live on the same path. Okay, x star and y star could be the endpoints of the same path if I don't have any control. And then by adding this edge, I wouldn't decrease actually the number. I wouldn't even get a linear forest. I would close a cycle. Okay, so this is say one of the reasons why really I want to rotate on disjoint sets. Okay, so this is kind of the dream case that I have disjoint sets of paths and really neighbors inside of them. But you'll see, I really can't hope for something in this in general, but you'll see later where this comes into play. So let me now kind of give you a general overview of the proof. And then I'll maybe go into some details and you'll see how I use this rotations of linear forests. So this is a very rough outline. So in the first part, I'll show you, we construct something which we call a linking structure, which is basically, you can think of it as something like an absorbing structure, which is just lives on a certain subset of vertices and is used to connect paths, okay? Then in the second step, so you have this absorbing structure. In the second step, we find some paths which cover the rest of the vertices. And then in the third step, we'll kind of integrate this rest into the linking structure to get the Hamilton cycle. So this was very abstract, doesn't matter. I'll now clarify all of the steps. So let's go. Let me briefly talk about the linking structure. So we always work in an expander graph, and I'll just define you what the linking structure is. I'll not show you how to construct it. Okay, so a linking structure is it's a subgraph of the expander which lives on some set X, and X has subsets A and B, and A and B are some polynomial size, let's say n to the 0.9. Let's just briefly denote the set A, the elements by A1, A2 till A and 0.9. And now the crucial property. So for any pairing of A and B, for any bijection from A to B, there exists paths such that the endpoints of the paths are really AI and the image of AI, and the paths are short. And not only this, these paths really span the set X. So these paths are spanning, and these paths are disjoint. So let me now just repeat it briefly on the picture. So I have some two vertex sets A and B of size n to 0.9, and you give me any pairing you want. So for any pairing, I can do this inside of this graph. So you give me the pairing, and I find you disjoint paths between the pairs which you want. So the paths are disjoint, and the paths are really spanning X. Okay, and the paths are short, let's say some logarithmic size. So is this definition of the linking structure clear? So are there any questions?
So why do you care about making your paths short?
Otherwise, I'll not have any control about what. So basically, I'm trying. I don't really care about making them short. So they could possibly be even of size polynomial, but just polynomial so that I don't take a huge fraction of the remaining vertices. So this may doesn't play a huge role.
So I have a
But
question.
just to have some control to understand, let's say, what the size of X is.
So maybe I don't understand the definition. So A and B have size n to the 0.9, and then
Yes.
every path only has like polylog n vertices in it. So how do how do the union of the vertices get you size xn?
It's not n. So X is a subset of the expander, of the vertices of the X. There's some vertices which are remaining.
Oh, I see. Okay, thanks.
Yes, so thank you. So basically you can see that the size of X is n to the 0.9 times the size of the path, roughly. Okay, so it's just a substructure which I find inside of the graph. I can find these paths which are short, but they don't really have to be short, I think. Yeah, it's not necessary that these are short. Okay. So please ask if this is not clear. Okay. So now let's say I have this linking structure, and I'll not tell you how to find it. It's basically an application of this extendability method, and using some sorting networks which were known much before. So I'll not go into any details about this. So it's a technical part of the proof, and it can be done, and it's not really our contribution that we did it. So it's kind of a slightly technical but simple construction, and it's already been utilized in finding trees in expanders recently in work by Hyde et al. Okay, so suppose now you have this linking structure, and suppose you can find these red paths here. And what are so there's no coloring in our graph, but these red paths just denote paths which have internal vertices which are outside X, so they're in G without X, and such that their endpoints are really A union B. So the paths live outside, and just the endpoints are inside of X. Okay, and suppose you can find such a collection, and you really cover this A union B with such paths. And suppose additionally, so now suppose you have something like this. Suppose the red paths really span G without X. So every vertex in your expander is already in this picture, which I drew you here. Then I claim you are done. Then you can find your Hamilton cycle. And why is this the case? So I drew the paths here in a specific way, but it's really so there's no assumption here. So basically you can always reorder the vertices in A and B such that the picture looks like this, because either the paths go across, so one endpoint in A and one endpoint in B, or it's both endpoints in A or both endpoints in B. So you can reorder the vertices so that the picture looks like this. And then you can use this property, which we have from before, that you can pair up these vertices inside of X with paths in any way you want. And the way I want specifically is for every vertex, I just go one vertex down until this last vertex, which goes up. Okay, and then you see here that I'll have a Hamilton cycle. So I can just wrap around like this, go here, and you can see that I get a Hamilton cycle. Okay, so if I was able to find these red paths, then I would be done. And these red paths are spanning. But I actually can't. Yes?
Sorry. So were you assuming that you are able to find this X and A and B with the property you mentioned in last page?
So I can find this X, and so this I can find. This is no problem. But I can't find I can't find the spanning red paths.
Okay.
So I can't find them, at least not immediately. But what I can do is to find these red paths which are of certain length, let's say n to the 0.1/10. And this is again this extendability method, Friedman-Pippinger embedding. Okay, so, and just to give some context, recall that the size of A was n to the 0.9. So the red paths will span a linear fraction of the rest. Okay, so this times this, so we'll have a fraction 1/10 vertices covered by those red paths. Okay, so this is what we can do. This is what we do as a first. So now to give you the second step, so let's say you have this, we already found the structure, and then you look at the rest, and then one part of the paper does actually the following. So you look at the rest of the vertices, and then I want to cover the rest of the vertices with few paths. And few will mean for me just a smaller polynomial than the size of A. So let's say n to the 0.8 paths. Okay, so this is, you have to work for this, but I'll not go into details how you do it. So just now, for now, assume that you can span the rest with few paths. And then just to rearrange the picture, or actually to say something before. So if you look at these paths in the rest, if I could somehow integrate them into the red path, then I would be done as before. So if the red paths were spanning, then I would be done. So if I can integrate this inside of the red path, I would be done. And now, okay, just redraw the picture. I have these black paths, I have the red paths. Number of them is n to the 0.9, number of them is n to the 0.8, and I want to integrate this into this. And now again, redraw the picture. So I split, so the number of vertices in the red path is linear, as I said. So I can split it just into two parts because the paths are short. So I can split it into two parts such that both of them have linearly many vertices. And then I can again do this cleaning procedure such that I can get expanders again on linearly many vertices. And recall that this would be the dream case. If I could have somehow a vertex here which goes to the first expander, so goes to the first expander, and the vertex here which has a neighbor in the second expander, I would be in the dream case where I can do my rotations separately and then kind of find an edge which decreases the number of paths. But this we can't really hope for. This is dream case, and usually you don't live in a dream, so you have to work for it. So let's see how you can actually technically do it. So instead of splitting everything into 2 parts, we split everything into 4 paths, say, parts. So I split everything into 4 parts, and I want to do a similar procedure. And now what one can do is I don't have control where the neighbors of these endpoints are. If they were in these, if they had neighbors like this into the expanders, I would be done. So I don't really know where the neighbors are. But what I do know, because my graph is an expander, I know that I can start with some vertex. So okay, let's say we first do the cleaning. I clean this set to get my expander U1. I clean this set to get my expander U2. And I take this vertex X. And I know that I can expand from X in this posterior rotation, just doing posterior rotations like I showed you in the beginning, without having any control where the neighborhoods go. But I know that I can reach this set U1 by just doing uncontrolled, almost arbitrary posterior rotation. So arbitrary means just uncontrolled. But I can reach U1. So what this means, there is a K rotation, say, so that I start with X, I maybe rotate to this path here, Y, where Y is maybe, then I rotate to the 3rd set, maybe I rotate to the 4th set, then I rotate maybe to the 1st set, but I don't go to U1, I just go to some vertex here, but then eventually at some point I will be able to reach some endpoint in the first expander. So this I can do just by using simple rotations. And I only use log steps to do it. Okay, the same I can do for Y. So I can arbitrarily rotate from Y to reach this set U2. So I do arbitrary rotations just not to clutter the picture. Maybe I go to the 4th set and then I immediately maybe go to the 2nd one. Okay, so I reach this endpoint X star and I reach this endpoint Y star. So I use K rotation, so the only endpoint changes is X and Y are killed. I got X star and Y star. Okay, just to simplify the picture a bit. So I did some rotations. I got to X star and Y star. And one important thing to observe here, because I'm doing just log n many rotations, because I'm expanding, I only need log steps to reach basically any vertex I want. So I can only, I can do this rotation by just touching logarithmically many paths. And these paths are of length n to the 0.1, if you remember, which basically means that I have many vertices remaining here, which are still fresh and were not used. And, okay, let me try to move this. Okay. So why are we not done here? This is also a question. So now I have X star and Y star inside of expanders. Why am I not done? The point is, while doing these rotations, because they were so uncontrolled, maybe I connected some paths from the first expander and some paths from the second expander, and now say X star and Y star might live on the same paths, or more generally, these expanders might live on the same paths. So it can happen that the structure in the end, like after these rotations, looks like this. And this is not the dream scenario. So now doing rotations in overlapping sets is technically not possible. So we have to work more. So not all is lost. So this is why we have these 3rd and 4th sets. So now, because I just used a few vertices here, I still have linearly many vertices in the 3rd and 4th set, and I can clean for expansion, so I get these new expanders in blue. And what I can do now is I do these, so U1 is an expander, so I can just rotate inside of U1. And because U1 does not touch any paths which are blue, So remember, these black vertices are the vertices which I used for rotations. There are few of them. So U1 and U2 definitely don't touch any paths which are here. So I can start rotating inside of this set U1, and I can reach a linear size set Sx. And then because it's linear sized and the blue vertices are also linear sized, I can find an edge in between. And you see, so I can rotate, I can change X for X star, and then I change X star for some vertex here, and then I change this vertex for X prime. And I can do now, after doing this, I can do the same.
Is your screen is frozen maybe? Because we don't see any blue paths or blue vertices.
Slides didn't change for us. You should be aware.
Oh, this is annoying. So nothing changes now.
Nothing, right? So we're still on the picture where U1, U2, and the black points.
This is very annoying. I mean, I don't know. Maybe I can stop sharing and then share again.
Share again, yes. Try to do this.
Can you stop sharing?
And then start sharing again. Okay. Okay. Very good.
How much did I say? Okay, so here was where it froze.
Here we saw it, and after that.
Okay. So this is not the dream. This I maybe convinced you. And now I clean for expansion in the remaining part. So now I get these blue sets.
Right.
Okay. Fine. So I got now these blue sets, and now I want to reach these blue sets so that I can rotate independently, and as I was trying to explain. Okay, so I rotate from inside of this U1, I rotate from X star to get a linear size set Sx. And then because I have a linear size set, I can jump to this blue expander. Okay, then I can do the same thing for Y star. I can get this set Sy here, and I can jump to the second expander. And the point is, because these things were completely independent from the blue things, there is an edge between. So this now is the dream case. So X prime and Y prime live on disjoint sets. So I can now start rotating and remove X prime and Y prime as endpoints. So just to say globally what happened, I changed this endpoint X for this endpoint X star, and I changed Y for this Y prime, sorry, X for X prime and Y for Y prime. And now I can find an edge. So I can do the rotations here and remove X prime and Y prime completely as endpoints. So what happened is just I killed two endpoints.
Sorry, I didn't quite understand. What's the difference between this dream case and the former case, which you said it's not good?
Yeah, so I was trying to explain this when the slides were running. So the point is here in the dream case, these rotations are, so the rotations we are doing is completely separate paths. So I do rotations in the third expander, I do rotations in the fourth expander. Okay?
Yeah.
And then I can find the edge which bridges, and it's fine. And I'll not close a cycle. But now if I did it here on U1 and U2, in order even to get to them, I maybe, these rotations maybe can connect some paths. And then when I try to rotate inside of them, when I close, maybe I close a cycle, for example. So I really want. So here, the most important thing is these things are completely fresh. Nothing touched them before. And as soon as I enter them, so I get two disjoint sets of paths, and then I can finish with in the dream case. Okay, so just now, what is left to do? Maybe we can, if there are questions, you can ask maybe later. But just to argue why you can do this, so here you just remove two endpoints, and now in order to finish the proof, I have to argue that I can repeat this procedure n to the 0.8 many times. Okay, and this is simple to do. So each part has n to the 0.4 or n to the 0.9 many paths. So each part has linearly many vertices. So n to the 0.9 many paths, and each of length n to the 0.1 over 10. And in each step, we use k rotations where k is less than logarithmic. Okay, so we only touch logarithmically many paths. So these black paths, which we touch by doing some rotations, the number of them, or let's say, so the number of these paths which we touch is the number of steps we do, so at most n to the 0.8, so n to the 0.8, times the number of paths which we touch in each iterations, which is at most logarithmic. And in the beginning, in each of these blobs here, I have n to the 0.9 many paths. So I really just touch a very tiny proportion of the vertices. So actually, every time I try to do this procedure, I have linearly many vertices in these paths here, so I can actually iterate. And again, do the same procedure. Yeah, I'm slightly over time, so I guess I'll stop here. Thank you.
Thank you very much, Nemanja. We can give Nemanja the round of applause for the nice talk. Questions, please.
So I have a question. Could you go back to the former pages? Yeah, here. So if X will have some neighbors in either of the four big clusters.
Yes.
Y will also have some there. I didn't understand. So, no, were you saying that no matter how X is connected to the four clusters and how Y are connected, you can always fix any of them to be U1, U2, and then somehow connect X to U1, Y to U2 by rotation.
So I have these four clusters. I clean for expansion in the first two. And then the point is, so forget now about any cleaning about anything. So I start from X inside of this graph, which I have, which is basically a linear forest, and I start doing rotations. Like in the postal rotation thing, I first have D
So
neighbors.
you forget about the clusters, you just do rotation.
Yes, I completely forget. Just remember that there is some U1 and U2, and these are the sets which I want to reach. And basically, by just arguing from expansion, so in the first step, I see D, in the second step, I see D squared, D cubed, and so on. I continue. So I'm now using the notation with D, but it doesn't matter. So after log many steps, because I'm in an expander, I'll also see U1.
Yeah.
So expand until you see U1. So there is some path in terms of K rotation, which will end up in U1.
I agree.
Yeah.
And Y will go to U2. But then in this process, X and Y only touched still n to the 0.1 potential linear paths in U1 and also in U2. Why not just to do it in the rest part of U1 and U2?
Maybe I think I understand. U1 is no longer expander. You're destroying expansion property, right? So expansion property means every vertex has so-and-so neighbor. So once you're changing it, whatever interior expander you need, it might not be there, right? So you cannot
okay.
Plus you can connect the process of U1 and U2 in one block. They no longer live on disjoint path. So you kind of mess a little bit picture. That's why you want to go to U3 and U4.
So U3, U4, you never change. You just say that this path you never want to use again. So the graph is still the same. So you can keep the expander property. But U1, U2, you keep on merging new part edges inside.
Maybe it was not clear. So it's not really. I in every step I find the expanders again. It's not really. So these expanders are just for one iteration. And the expander, it's a good question. So basically, when I do I remove X and Y as endpoints, and then let's say I use these black things. And then again, when I want to do the same procedure, I again find a new U1 and a new U2, which are expanders inside of these sets. So
but
I start.
What?
I start with fresh expanders.
But then what's
That's
the point of U1, U3, and U4? I still didn't get.
just to have expansion. So I can't. So maybe like there's some technical details, but say you want U1 and U2 so that you can expand. So here you want to expand, but by not touching the blue things. So the blue things you can imagine there. I want to do the dream. Blue skies, everything is fine. I don't want to touch it. But then I use these U1 and U2, these first expanders, so that I can expand there independently from blue.
Why is red not green?
Why is in order to get
Let's this technical thing we pass to offline discussion, because I want to give chance other people to ask questions.
Oh, sorry. Okay.
Yeah. So more questions, please.
I have one question as well. When you do these steps of uncontrolled rotations, are you ever worried that the rotations for X and Y might collide? Do you need some robustness properties to make them avoid each other or something like that?
In some sense, yes. So not really. So you're not trying to avoid collisions in maybe the sense you're asking. So I first do the rotations for X. I change my linear first, and then I do the rotations for Y. I have to be maybe slightly careful by that. Yeah. So let me see if. So I think technically how we do is because I can avoid everything which was touched before, but yes, we are not doing it. So basically you can do it uncontrolled.
So essentially you're saying in this new one, I just do it uncontrolled for Y once and change the X and just do it in the new forest. Yeah, that makes sense.
So the only thing which is maybe I was cheating. So maybe it can happen that when I do the rotations for Y, I end up in the same expander as X, which is not good. But then I can actually use some expansion properties to do just one more step to end up in U2.
Okay, thank you.
More questions? So if not, maybe let's thank Nemanja again. Right? And we can stop the recording.